Moment distribution method. Let us solve the following example which we solved earlier using the slope deflection method. To review, in the slope deflection method, we determine the fixed end moments. We use the slope deflection equations. We apply equilibrium equations, and as a result, we were able to solve the end rotations and the end moments. Let us apply the moment distribution method to this beam problem. The first step is to determine the stiffness per member. Using the equation for EI over L, the stiffness for member KAB and KBA is equal to 4EI over L, or 5 equal to 0.8 EI. For member BC, the I is 3 times 3I, hence the stiffness for KBC and KCB is equal to 4 times 3 EI over L equal to 7.5, giving me 1.6 EI. Next, we determine the distribution factor using the equation the stiffness of the member divided by the joint stiffness. For member AB, take note that joint A is a fixed support. Hence, using the definition of distribution factor, the dF of member AB is the stiffness of member AB divided by the joint stiffness, which is the stiffness of the member plus the stiffness of the wall. But the stiffness of the wall is equal to infinity, hence dF will be equal to 0. Next, the distribution factor for member BA is equal to KBA divided by the sum of the stiffnesses of the members connected to BA corresponds to joint B corresponding to BA and BC. So 0.8 divided by 0.8 plus 1.6 equal to 0.33. Similarly, the dF of member BC is equal to KBC divided by KBA plus KBC, giving you 0.67. For joints, for KCB, that is a roller, so the stiffness of or distribution factor for CB is equal to KCB divided by the stiffness of the member connected to joint C, which is also CB, so hence giving you 1.0. The moment distribution method uses a table which is as shown. In the table, you have to first define the joints. In this problem, there are 3 joints, A, B, and C, where joint A corresponds to 1, this is B, and this is equal to C. So there are 3 joints, A, B, and C. The second parameter is the member. The members connected to joint A is member AB. The members connected to joint B is BA and BC. And the members connected to joint B is CB. We have already computed the K. We also computed the distribution factor earlier. Another way to compute the distribution factor is simply using the equation. So K for member AB, K divided by the joint stiffness, which is infinity, giving you equal to 0. For member BA, the distribution factor 0.33 was obtained by simply using the equation point A divided by the sum of the stiffnesses connected to joint B, which is equal to 0.8 and 1.6. So 0.8 divided by 2.4 will give you 0.33. For BC, 0.67 was obtained by using the equation 1.6 divided by 0.8 plus 1.6 or 2.4, giving you 0.67. And for CB, this is equal to 1.6 divided by 1.6, so equal to 1. Next, we compute the fixed end moments. The fixed end moments for member AB is using PL over 8, and you have 0.62.5 negative for AB and positive for PA. For BC, we use the equation WL squared over 12, and we have negative 93.75 and 93.75. These are now the fixed end moments. Next, we apply the balancing moment. The balancing moment is determined by simply multiplying the unbalanced moment multiplied by the distribution factor of that member. For AB, the unbalanced moment is negative 62.5. So we apply an opposite direction, 62.5 multiplied by 0, and you will get a balancing moment equal to 0. At joint B, the unbalanced moment is the sum of the moments applied at joint B, 62.5 minus 93.75. That is a negative value. So you apply a positive value of the difference, multiply it by 0.33, and you will get 10.3125. For member BC, the value 22.9375 was obtained by again getting the unbalanced moment at joint B, 62.5 minus 93.75, which is equal to negative 31.25. So 31, you apply the opposite direction. So positive 31.25 times 0.67 will give you 20.9375. For member CB, the unbalanced moment is 93.75. So apply the opposite moment, so negative 93.75 multiplied by the DF, which is 1, and you will get negative 93.75. That completes cycle number 1. The next step in the procedure is we apply the carryover moment. When we apply the carryover moment, we apply 1/2 of the moment at the other end. For example, this is for member AB. 1/2 of 0 is of course equal to 0. For member BA, 1/2 will go to AB. For member BC, 1/2 will go to CB. And for member CB, 1/2 will go to BC. So all of these are 1/2 of the values applied in the balancing moment, applied at the opposite end of the member. Next, we balance again. So the unbalanced moment for AB is 5.15625. Apply the negative and multiply it by the DF. Again, it should be 0. For joint B, the unbalanced moment is 0 minus 46.875. So apply the opposite direction, 46.875 multiplied by 0.33, you will get 15.46875. And 46.875 multiplied by 0.67, you will get 31.4025. And for joint C, since this is a pin, we simply apply the same moment with opposite direction. That completes cycle number 2. Cycle number 3, you apply again the carryover moment. AB will go to BA, BA will go to AB, the half of the moment. BC will go to CB, and CB will go to BC. And then balance again, and you will complete cycle 3. You repeat for several cycles, in this case up to 5 cycles. After 5 cycles, the final end moments can be obtained by simply summing the moments from cycle number 1. Take the summation of all these moments, and you will get the end moment for AB. And similarly for BA, take the sum of all these moments, and you will get MBA. And this one, take the sum and you will get MBC. And similarly, take the sum, you will get MCB. Okay. You can compare. These are the values using the slope deflection method, and of course there will be a difference because the moment distribution method is a numerical or iterative method. One way to check the equation is that at joint B, we have BA and BC. The sum of these moments should be equal to 0. So using these end moments, you can now determine the end shear, solve for the reactions, and then draw the shear and bending moment diagram. This is the same problem, but using 10 cycles just to illustrate the difference in answers. You will notice that there is not much of a difference in the final moments using 10 cycles. You can apply the moment distribution method using Microsoft Excel by using a simple formula for the iteration, and you can easily apply several cycles of uh, implementation of the procedure. These are video tutorials. If you want to learn more about moment distribution method, these are some suggested links for tutorials. And if you want to automate the moment distribution method specifically for your problem set, you can watch this video. They're also available online resources in the internet. Thank you very much for your attention.